What the heck?
Tagon.
Sup, fam? It's really hot today. It's been like 50 degrees for all of May, and it snowed in May, where I am. Which, given that no one knows where I am other than I said the East Coast, it's surprising that it snowed in May here. It never snows in May here. And now it's 80 degrees. And so I'm schwitzing. This is a little addition to two videos that I did recently, which I will link to as I cover the little additions. There's two of them, as I just said. They're sort of, not clarifications, but, additions is probably the right word, because one of them is going to be actually figuring out the recursion formula from one of my recent videos, and the other one is going to be explaining how the residues actually all cancel in the recent Wacky Calc Wednesday that I did. So, without further ado, let's do it. Get out of here, Bernoulli. You're not till later. Alright. So what are we going to start off with? First of all, let's talk about the video I recently did called the W gamma connection. So let's recall a couple definitions, right? This was the video I did. There's the link to it. So what did I prove in that video? I proved that, if we know that y is equal to x times e to the x, then we have the definition of the w function as the inverse of this, so w of y is equal to x. So this is the definition of the Lambert w function. It undoes this function here. What I proved in this video, the w gamma connection, was that the integral that I'll call I of x from negative e to the negative 1, or negative 1 over e, to 0 of negative w of u to the x minus 1 du was equal to this integral here from 0 to 1 of t to the x minus 1 e to the negative t dt minus that same integral but at x plus 1 instead of x. So 0 to 1 of t to the x times e to the negative t dt. And these are the lower incomplete gamma functions, so this was possible to rewrite as little gamma of x comma 1 minus little gamma of x plus 1 comma 1, and because of the recursion formula for the lower incomplete gamma function, we were able to show that this was the same thing as 1 minus x times gamma of x comma 1 plus 1 over e. So this integral over that little bit of the w function that's to the left of the y-axis, made positive and then raised to real powers, gives you this function right here, sort of in terms of a gamma function. And someone in the comments, I can't remember their name, but I'll put the comment right here, was quite astute in telling me what the recursion formula for what I of x was, and I'm simply going to prove to you what it is today, because I didn't actually know what it was at the time of making the video, but it's quite easy to show, if just plugging in 1 and 2 into here, that I of 1 is equal to 1 over e, and I of 2 is equal to 3 minus e over e. Now 1 over e is about 0.367, I think, and 3 minus e over e is about 0.103, which makes sense because this is actually a decreasing function. So when you see it, it's quite clear that it should be something around there. Like if you plug this into Desmos or something like that, it's actually probably easier to plug this in, because loading a closed form expression for the w function requires another integral that I'm going to prove in another video. So this actually is a very inefficient way of plotting this function. So you would be better off plotting this, and it will equal that. Promise. In fact, you don't have to believe me. I proved it in that video. Now these are the first two sort of seed values. This is undefined at 0. So negative w of u to the power of negative 1 and integrating over that is actually undefined. It's an infinitely large area, and so you need these two things as your seed values to do the recursion. So let's prove the recursion formula. So what it is that we want to do is we want to take a look at I of x plus 1 and see if we can reformulate this into something in terms of I of x, because then we can use previous answers to inform later answers, which is quite, the way that recursion usually works. So we know that I of x is, what did we say this was equal to? I'll just erase those. Given that we know the definition of the lower incomplete gamma function, we learned that this was equal to 1 minus x times gamma of x comma 1 plus 1 over e. So I of x plus 1 is equal to the quantity 1 minus the quantity x plus 1 times gamma of x plus 1 comma 1 plus 1 over e. So all we did was just plug in x plus 1 wherever we saw an x, right? Because that's how functions work. And now we're going to sort of try to manipulate this expression into being something in terms of I of x, which was just 1 minus x times little gamma of x comma 1 plus 1 over e. So first let's simplify this little expression. So we get 1 minus x minus 1, so that's just negative x, right? So we have negative x, but we also have gamma of x plus 1 comma 1 here, so we can break this down using the recursion formula for the little gamma function, or the lower incomplete gamma function. And that comes out to this, right? So this becomes x times gamma of x comma 1 minus 1 over e. If you don't understand why, just go back to my previous video on this subject and I show that this is the case using integration by parts. And then we have this plus 1 over e on the outside. Now what we're going to do is we're going to multiply this negative x in, and then we're going to use an extra factor of something to try and get I of x to come out of it. Because remember, I of x, let's just recall, so we know what we're looking for. We're looking for 1 minus x times little gamma of x comma 1 plus 1 over e. We want to make this appear in our equation somewhere so that we can call that I of x, and then we have I of x plus 1 in terms of I of x. So let's do some manipulations. For example, let's distribute this negative x in. So we end up with negative x squared, right, times gamma of x comma 1 minus x times minus 1 over e is plus x over e. So we'll do plus x plus 1 over e, right? Because this is just going to be x over e plus 1 over e. So plus x plus 1 all over e. And now what we're going to do is we need to somehow make this factor appear, which is quite easy. All we have to do is multiply this by that factor and divide it by that factor, and then we don't have to worry about it. So we're going to multiply it by the factor 1 minus x, and we're going to divide by the factor 1 minus x. Okay? That's what we're going to do. And now, whoops. And now, we're going to multiply this onto here, which is going to give us x squared minus 1, because it's a difference of squares. And we're going to use this negative to flip the factor when we multiply it onto here, to make this x squared positive. And you'll see our formula appear from nowhere. So let's erase this and distribute. So we end up with negative x squared times x minus 1 times gamma of x comma 1 plus x squared minus 1 over e all over x minus 1, right? Because this was the x plus 1 in the numerator times that x minus 1 that I just factored in. Now we're going to use this negative to flip this difference. And we're going to break this up into x squared over e minus 1 over e. And now we're going to factor the x squared out of here. So the x squared comes out the front. And you'll notice there's our expression for I of x, which is absolutely brilliant, because now we can just say that this is equal to x squared times I of x minus 1 over e divided by x minus 1. I hope that's visible at the bottom of the screen. The little record symbol is in the way, but I think you can sort of see that at the bottom, right? So this is I of x plus 1. And you'll notice we can't plug in 1 to find out I of 2, because we'll end up with 0 divided by 0, so we'd have to use L'Hopital's rule. But you can avoid that altogether by simply deducing what I of 1 and I of 2 must be. So if you recall, we said that I of 1 was equal to 1 over e, and I of 2 is equal to 3 minus e over e. And so to find I of 3, you simply plug this into there, and you get a nice recursion formula. You can actually sort of write all of the integer outputs, or the outputs given integer inputs in terms of different factorials and the choose function, etc., etc. So this was the recursion formula that I didn't have in that video, and so here's the answer. Thank you very much for the person in the comments for making me aware of this. It's a beautiful little formula. The second thing I wanted to address was a part of the Wacky Calc Wednesday video that I recently just did, where I showed this result, that the integral from negative infinity to infinity of 1 over e to the t minus t all squared plus pi squared dt is equal to 1 divided by 1 plus omega, which is, I think, about 0.638, where omega is defined to be w on the principal branch of 1, which satisfies the relationship 1 equals omega times e to the omega, right? And so omega is about 0.567. Right, so this was a neat constant, and this was a beautiful result, a truly remarkable one, as I think I called it in the thumbnail. But I left a step open, sort of, in the process of proving this result that I sort of brushed off to the side because I felt that the video was going long enough. And that result was that every single residue of this thing, given this contour, being a semicircle in the upper half of the complex plane, all of the residues in here all cancel except for the single one at negative omega plus I pi, right? And that's the only one that matters in the entire sum, and all the rest cancel. And that was sort of just said and stated, and then we just plugged in the only one that I said mattered, and we got this result. But why should you believe me? I mean, you can plug it in and see that it is in fact true, but why should you believe me? So let's actually calculate the residues, right? So we had all of those zk's plus or minuses, zk plus or minuses, right? That were equal to, how were they defined? They were negative w of negative k at 1 plus or minus I times pi, right? Those were each of the zk plus or minuses, right? So you pick plus or minus and you pick a k, and that's the residue, or that's the pole of the function that's within the semicircle contour. So what we're going to do is we're going to calculate a residue at any given one of these zk plus or minus e's. So the residue of this being f of x under the integrand, or f of z, I suppose, f of z at z equals zk plus minus is equal to, sort of by definition, the limit as z approaches zk plus minus of the factor that causes that problem, z minus zk plus minus, divided by e to the z minus z all squared plus pi squared. Now, because plugging in zk plus minus into the top and in the bottom will cause 0 divided by 0, we have to use L'Hopital's rule, which means we have to differentiate the top and the bottom, and then see if we can apply the limit. So the derivative of the top with respect to z is just 1, because the derivative of z is 1, and the derivative of a constant is 0. So we end up with the limit as z approaches zk plus minus of 1 divided by, what was the derivative of the bottom? It was 2 times e to the z minus z times e to the z minus 1. And now we can plug in zk plus minus, because none of these are going to be made 0 by that. And we get 1 over 2 times e to the zk plus minus minus zk plus minus times the quantity e to the zk plus minus minus 1. So that's our residue, and now we just need to sort of foil all that, not foil it out, but like expand it out and see what we end up with. Remember, when we add up all of the residues, we're going to be multiplying by 2 pi I, so you will see a factor of 2 pi I in the denominator here, which would be canceled to result in just this answer here. So we plug in this representation for zk plus minus. Yeah, so let's do that. So we end up with 1 over 2 times e to the negative w sub negative k of 1 times e to the plus or minus I pi minus or I guess in this case plus, because this negative is gonna cancel with this negative here. So we get plus w sub negative k of 1. And then the minus and this are gonna swap, so we're gonna get minus plus I pi. Let's move this one more to the center once we finally have a center. And then we have, again, e to the negative w k, or minus k, sorry, negative w minus k of 1 times e to the plus or minus I pi minus 1. And now we can sort of see where to place the 1. There we go. And now I showed that this was equal to just w of negative k 1. This is equal to negative 1. And so a lot of things drastically simplify. So we're going to get 1 over 2 times w sub negative k of 1 times negative 1, so that negative actually comes back, right? Because e to the plus or minus I pi is negative 1, plus w sub negative k of 1 minus plus I pi. Again, this is just w sub negative k of 1, and this is just negative 1. So you get negative w sub negative k of 1 minus 1. These cancel because they are negatives of each other, and this negative here, this factor of negative 1, will flip this minus plus here. So it becomes w sub negative k of 1 plus 1, and then it becomes plus or minus I pi, and then we can factor out that plus or minus I pi, which gives us 1 over plus or minus 2 I pi of w sub negative k of 1 plus 1. And here we can see why the residues of all of the k's except for the 0 branch, the principal branch, will actually cancel. Because you're going to have, once you pick k, that just chooses this here. And then you pick plus and minus, and you end up with, we can just put this plus and minus in the numerator, right? You end up with a positive version of this and a negative version of this, and we're adding them all together, right? Both the plus and minus version of all of the k residues, except for the 0 one, appear inside of this contour. And there's only the plus version of the 0 branch, the principal branch, actually appears in that semicircle. The other one does not, and so it's the only one that's left. Because of this plus or minus here, you're essentially just saying, here's one of the k residues, here's the negative of that k residue, and then they cancel. And the only one that's left in the end is the principal branch, or k equals 0. And so that's why, to answer this person's question, why all of the residues cancel. I guess that wasn't too hard. I could have put that in the other video, but here's another video for everybody to watch now. So thank you very much for watching these little additions to my previous videos. I cannot wait to show you this other integral that I want to prove, resulting in a beautiful expression for the Lambert W function. Probably one of my favorite integrals ever. It's just a beautiful thing to try and solve. It's also contour integration and using residues and all that, and it's just wonderful. So I can't wait to show it to you. That'll be the next time we do a Wacky Calc Wednesday. Enjoy the almost summer heat, everyone.